Okay, this video is about looking at chemistry as the science of watching large volumes of atoms. In order to do that, we're going to have to learn how to address atoms in large numbers. So, a guy named Avagadro said, I have an idea. Let's take carbon, then imagine that you have exactly 12 grams of carbon. Okay. Then how many atoms would it take to match 12 grams of carbon? That's given as Avogadro's number. It would take this many atoms. And that's really cumbersome to write, so we would rather write that in scientific notation, or about 6.02 times 10 to the 23. Okay, so this is where Avogadro's number comes from. It's the idea that if you pile on a bunch of carbon atoms until you get exactly a measure of 12 grams, you have that many carbon atoms. So now we can introduce you to a new unit of measure. Now, I've mentioned before that you could throw a bunch of atoms in a box and say, I have 1,000 atoms in a box, and I'll call it a certain name. You could call it a Susan of atoms, or you could have 1 billion atoms and then call that a Ralph of atoms. But instead, we're going to call this exactly this many, we're going to call it a mole. And it doesn't have to be atoms. Now we can address moles in any other context. So we could say, I have 1 mole of hydrogen atoms. And then that would mean I have 6.02 times 10 to the 23 hydrogen atoms. I could say, no, I have 1 mole of hydrogen molecules. That would mean I have 6.02 times 10 to the 23 hydrogen molecules. If I combine those with some oxygen, then I could end up with 1 mole of water molecules, or 6.02 times 10 to the 23 water molecules. Now you're starting to get the hang of this. Hopefully you're okay with being absolutely ridiculous with this, because if you have a mole of cats, guess how many cats you have? 6.02 times 10 to the 23 cats, right? Mole. That's just a counting number. Okay guys, we got this chemical equation here, and it might look a little bit on the scary side, but we can break it down. We can look on our periodic table here and see iron down here, number 26. We can see oxygen over here, it's number 8, and then carbon is pretty close to it over here, right? So all we have to do is just develop some little marbles to represent the number of iron atoms before the arrow, before the reaction proceeds, and the number of oxygen atoms before the reaction proceeds. So we have this molecule here, this iron oxide molecule. This is actually just rust. And so we have here 2 irons and 3 oxygens in the molecule. And we also have a number out front telling us that we have 2 of those molecules, right? We have a carbon atom, but we have a number out front showing us that we have 3 of those carbon atoms. When we're done, we can see that we have 4 iron atoms, and then we have a molecule, carbon dioxide here, that has 2 oxygens and 1 carbon, and we have a 3 out front that shows that we have 3 of those molecules. Now, this might seem a little weird until we actually stop and think about this from the standpoint of the number of marbles that we have. So here, what I've done is drawn out the marbles so that you can see that there are 2 iron oxide molecules. So here's an iron oxide molecule. It has 2 irons and 3 oxygens, and then we have 2 of those molecules, 1 here and 1 here. So in total, we have 6 oxygen atoms and 4 iron atoms. here you can see we have 3 carbon atoms available, and so those will react in such a way, if we add a little bit of energy to this reaction, then we can actually produce new chemicals out of it. Now, what we have to do is know, if we know what chemicals are going to form, so we know we're going to get just plain iron and we know we're going to get just plain carbon dioxide, then we can rearrange our marbles until we get the correct number of them. So we know we have 4 iron atoms available ahead of time. So when we get pure iron out, we know we'll get pure iron and we'll get 4 atoms of it. And the same goes for if we have carbon dioxide here. This is a carbon dioxide molecule, and so if we have 3 of them, then that shows that we would have to put a 3 here because we need to make sure we have 6 oxygen atoms and 3 carbon atoms, and that's satisfied by this set. So we haven't lost any marbles or gained any marbles. We've got the same number of marbles. How does that relate to our large number, Avogadro's number? Well, if this is true for 4 iron atoms and 6 oxygen atoms and 3 carbon atoms, it is also true for 4 moles of iron atoms. And so we can actually look at this in terms of moles. What we can do is say 1 mole, and remember, if you have a mole of cats, you have 6.02 times 10 to the 23 cats, right? 1 mole of rust is not enough, right? Actually, I put 1 there. I should put 2 there. 2 moles of rust, that's enough. 2 moles of rust, it actually, you can write it out like this, but for shorthand we write like so. 2 moles of rust plus 3 moles of carbon can produce, plus a little bit of energy, can produce 4 moles of iron plus 3 moles of carbon dioxide. And so if you can get atoms to work this way, you can get moles to work this way. And the reason that we do that is because honestly, you're much more likely to work with a gram of carbon or 3. If this is 3 moles of carbon, you have 3 gram, or actually you have 3. There's 12 grams of carbon in a mole, so you'd have whatever 3 times that is, grams of carbon. So this way you can say, what is that, 36 grams of carbon? Yeah, something like that. So 1 mole of carbon is 12 grams, so 3 moles of carbon would be 36 grams. And that way you can make sure that you have, you know how many atoms roughly that you have by weighing it on a scale. It's hard to measure 1 atom on a scale, it's easy to measure 1 mole of carbon on a scale. So that's why we use moles. They're big. Okay, now this is going to remain true for solutions. Now solutions are typically like a glass of water is if you put stuff in there you get a solution. So we're talking on the order of moles, and so there are ways to measure this out carefully. And we don't want to go into too many calculations because we've kind of run out of time this semester. So my goal is to make sure that you're clear about what moles are and you're clear about what the science is behind solutions so that later you can do the math if you need to. So a solution. A solution is essentially chemicals dissolved in water. I mean, if you really want to make it a simple definition, and I do prefer the simple definitions. Chemicals dissolved in water is solution. So if you say a saltwater solution, then essentially what you've done is you've taken salt crystals, put them into water, and they've dissolved. They have to dissolve or it's not a solution. Now that's a little bit overly simplified because it doesn't have to be water that is the solution. You could use alcohol as a solution, you could use oil as a solution, you could use acetone as a solution. There's all different kinds of ways to make a solution, but essentially when people say solution, they're usually referring to water. If you deal with an acid solution or something like that, you're definitely dealing with water. So our way of talking about solutions in general will be that if I take a glass of water and I take some salt crystals and I put the salt crystals into the water, then the water is my solvent. The salt crystals are my solute. And then when I put them together, then there will be a solution, a saltwater solution. Okay, let's take a close look at what happens on the atomic level here. So we've got little water molecules everywhere. And so originally I have just water swimming around in itself, and then I dump the sodium chloride in, the table salt, and the act of dissolving is actually a chemical process. So remember, this is what our sodium chloride looks like because it has an ionic bond, and this is immediately going to separate. But let's not forget, the sodium does not get to take its electron with it because it's already donated it to the chlorine. So what happens after that is they go their separate ways. Now there's some more action that happens with the water due to the fact that there are positive and negative ions floating around. But the gist of this is that the sodium and chlorine atoms are now ions floating around in the water. So I frequently see or hear people talking about terms that are not strictly used correctly. Of course, I don't go correcting them because I don't want to be pedantic about it, but if you say that acetone melts your shoes, then technically it's not melting it because melting is a physical process. Dissolving is a chemical process. Melting is just going from one solid state to a liquid state. What acetone will do to the soles of shoes is acetone becomes the solution, and the rubber in the shoes becomes the solute, and it dissolves. So really it's dissolving the soles of your shoes rather than melting them. By the way, don't walk on acetone with your shoes because it will stick the rubber of your shoes to the floor. So, and if you don't know what acetone is, fingernail polish remover, typical fingernail polish remover is a very diluted version of acetone. So we can begin thinking about these things in terms of chemical solutions. I'd like to go ahead and mention acids and bases and how that works using the concepts of solutions. So let's go through this process again, but instead of using salt, we're going to use something a little bit different. It's going to actually have the same kind of geometrical structure as water, but instead of an oxygen, it's going to have a sulfur. So this is hydrogen sulfide, and one of our members of class has mentioned it previously as a dangerous gas that is released in the process of drilling oil. So hydrogen sulfide let's go ahead and take this gas and dissolve it into our water and see what happens. So when we introduce this hydrogen sulfide into the water, an interesting thing occurs. This sulfur has the ability to interact with some of these water molecules, and it'll actually attempt to make a molecule that looks like this. Okay, so now what's important about this is that all of these hydrogens actually left their electrons behind. Also, this molecule is ionic, so we get this going on. But the important part is all of these hydrogen ions that we have released into the solution of water. Essentially, those are protons, right? So there's all these protons just flying around in the water. And what this does is it increases putting hydrogen sulfide into our water increases the potential for hydrogen. Or the pH. Now, in fact, it does not make a larger pH number. The scale's upside down, so actually it decreases the pH. It's a little weird, but the more H's you get in your solution, the more hydrogens you get in your solution, the lower the pH. pH essentially means potential for hydrogen, and it means that a very low pH has very many hydrogens in the solution, and a very high pH does not. Okay. Now, if you have such a solution, we call this an acid because low pH or high numbers of hydrogens is an acid. Now there's a reverse that we could do to this, and I won't go through the whole chemical process for the opposite, but instead we'll dissolve something else on the other end of the scale, like let's say sodium hydroxide. Now, there's a really interesting thing that happens when you put various solutes into water. Each of these molecules, H2O, can be separated into the following molecules. So when the hydrogens separate off of the water molecules, then essentially what we've done is we've theoretically broken this down into a hydrogen ion, or in other words, a proton that has been released from the water molecule, leaving behind an hydroxide ion. So what we've done is we've split this into protons and hydroxide ions. Now, these are very, very important in the production of acids and bases. If you put something into this solution that grabs the hydrogen atoms or the protons and binds them, then you will have this extra guy running around, right? But if you put something in that binds this, like we did previously, then you'll end up with a lot of this running around. The question is, which one are you going to have running around? The protons or the hydroxide ions? If you end up with a lot of these running around, as we saw, that's an acid. So we should put this here. Lots of protons running around. If we have this running around, then what we have is a base. So, essentially, we have determined what causes acids and bases, but how do we measure them? So, again, I've mentioned to you that a pH number is really about how many protons are running around. So if you don't have very many protons running around, that means you do have a lot of hydroxide ions running around. If you don't have a lot of hydroxide ions running around, it means you do have a lot of protons running around it. It's an either-or thing. So we put a scale together called the pH scale. Let's look at that. So here we have our pH scale, and there's actually some meaning to these colors. Although it's a little harder to read in real life, there is something called litmus paper, and if you dip the litmus paper into your chemical, then the coloration actually tells you which level of pH that particular chemical is. This scale goes from 0 to 14. It is possible to extend beyond that scale, but typically things will fall within this scale. Water at room temperature is at a pH of 7, which is considered the basis because water has just as many hydroxide ions as it does protons running around, and there aren't very many of them. But you can actually increase the activity of separating these apart and binding some of them by going either to the right or to the left. Highly acidic things are way down here, and highly basic things are way up here. This tells you that the more in this direction you go, the more protons you have, and the more you go in this direction, the more hydroxide ions you have, right? So this is the general idea behind acids and bases, and you can look up various things on the pH scale. It is important to remember that this is not a linear scale, so something that is a 3 is not twice as acidic as something that's a 5, just because it's just as far away from 7. So just because something is a 5 and something else is a 3 does not mean that the 3 is twice as acidic as the 5. It is, in fact, 100 times more acidic than the, well, on the order of 100 times more acidic than the 5. So this is not a linear scale. It's logarithmic in nature. Okay, that brings our video to a close. Hopefully this gives you a concept of solutions. Instead of doing a summary for this video and previous videos, I believe I'm going to do a separate video that summarizes the things that you're going to be interested in knowing.